In the previous lecture, we derived a governing equation for the shape of the meniscus. The equation for the height of the meniscus, that is h of x, was written in two forms. On the left hand side that you see on your screen, the capillary length explicitly appears, whereas on the right hand side, the capillary length has been absorbed in terms of rescaled variables, that is capital X and capital H. Now, we want to ask a number of interesting questions related to this meniscus. For example, we want to find out what is the height to which the fluid rises. That has been denoted by H0. I have highlighted it in yellow. That's the height to which the fluid rises. Now, what's the relationship between the contact angle and this height H0? Can we explicitly integrate this nonlinear ordinary differential equation to get the shape of the meniscus? Is there a simpler alternative? Instead of integrating this equation directly, can I come up with a simpler expression, because this is a nonlinear equation after all? We want a linearized version of this equation, sometimes because it may shed some insight into the shape of the meniscus. For example, we want to find out how rapidly does the meniscus decay from its height h0, and we finally want to understand why does the fluid rise at all. Can we get a simple mechanistic insight into that, into this in terms of, let's say, force balance? So we'll try to address some of these questions in this lecture. So let us begin by looking at the equation that I've written on the right hand side. So the equation that we have is hxx by 1 plus hx square whole power 3 by 2 is capital H. That's what we have. Now we can multiply the equation with hx. If we do this, then we have hx times hxx 1 plus hx square whole power 3 by 2 is h times hx. And the reason we do this is because if you let me make a rough sketch here, or rough notes on the side. So for example, if you compute the derivative of this quantity 1 by 1 plus hx square whole power half, this quantity will turn out to be minus hxx by 1 plus hx square whole power 3 by 2, right? And so therefore I straight away have the left hand side is d by d capital X of 1 plus hx square whole power half. That's the left hand side. What about the right hand side? D by dx of h square by 2 is exactly h times hx. So therefore this is d by d capital X of h square over 2. I can now integrate on both sides, and this gives me minus 1 by 1 plus hx square whole power half is equal to h square by 2 plus an integration constant c. Now let's look at the boundary conditions here. We said as x goes to infinity, h goes to 0. Further, the meniscus becomes flat and merges with the liquid bath far away from the plate. So the idea that we have is we have a large we have fluid in a container, and we're dipping a plate, and the fluid meets the interface meets the plate at an angle theta e, but far away you expect the fluid to not care about the plate, and it would merge with the flat interface far away. And as a result, you should expect the boundary conditions would be, in the far field, as x goes to infinity, we have both h going to 0, hx also going to 0, and therefore if we substitute this, if I have minus 1 by 1 plus 0 is equal to, and this gives me c equals minus 1. And therefore what I have is minus 1 by 1 plus hx square whole power half is h square by 2 minus 1. Or I'll rearrange it to simply write 1 by 1 plus hx square whole power half plus h square over 2 is equal to 1. Now this is an important result. We'll call this as equation. We'll call this as 1. Now there are two possibilities here to examine. The first thing that we will do is we can integrate this equation further one more time. But before we do that, let's examine, let's write this equation in a different form. For example, if you look at the shape that I've drawn, I have introduced one more variable, that is theta, right in the middle. And let me highlight that here for your benefit. This is theta in the middle. And what is this theta? This is the local angle measured from the vertical, the angle that the tangent to the interface makes with the vertical. Now, as x goes to 0, this theta becomes equal to theta e. So at any arbitrary location theta, what we have now is a situation as follows. We have an interface here, and at some arbitrary x, the angle is theta. And now I can actually measure, let me make the drawing a little better. So at any arbitrary location here, if I say this is delta x and this is minus delta h, the change in the height of the meniscus between these 2 points, then I have cot of theta will be dh by dx, and therefore that is minus hx, and therefore I have 1 by 1 plus hx square whole power half is nothing but 1 by 1 plus cot square of theta power half. In the denominator we have a cosecant square theta, the square root of that, which is 1 by sine theta, 1 by cosecant theta, and this becomes sine theta. So what we have now is 1 by 1 plus hx square whole power half is sine theta, right? And so I can also write this expression as sine theta plus h square over 2 is equal to 1, or h square over 2 is 1 minus sine theta, and this implies h becomes square root of 2 into 1 minus sine theta. This is h at any arbitrary x. As x goes to 0, capital H of x becomes h naught, and therefore I have, and theta becomes equal to theta e, and therefore I have h naught is square root of 2 into 1 minus sine theta. I can also write this in terms of the dimensional height, and that dimensional height is h naught of small x, essentially becomes 2 gamma by rho naught into g times 1 minus sine theta. So we now have the height to which the fluid has risen. So this is the height to which the fluid has risen. The point at which the fluid makes contact, h naught, is now given completely in terms of capillary length and the angle, the contact angle at the wall, right? So this is, let's call this as equation 2. But we can also do one more thing, which is to directly integrate this equation. I will not go into, well, by the way, this is not h naught of x, a small correction here. This is h naught at x equal to 0. So there's also one more important thing to understand. This equation here that I'm highlighting, this is also the shape of the meniscus, because it tells me what is the height at any given x as a function of angle. So you can think of this as a height versus angle coordinates. Now we can also integrate this equation. Which equation? Equation number 1. So we have integrating equation 1 for h of x. Note that we still have not, in this we have only used, to get equation 1, we've only used the far field condition, that is x going to infinity. Now we can actually use the other condition. What is the other condition? Using the condition as x goes to 0, h goes to h naught. Okay, if we use this condition, then I will not, this is a little tricky, so I will not spend time on trying to derive this equation, trying to do this integration, but essentially what we get is 2 by h minus cos hyperbolic inverse of 2 by h naught minus 4 minus h square plus 4 minus h naught square. Note that here we have x in terms of h, not h in terms of x. It's difficult to get an explicit expression for, it's not possible to get an explicit expression for h of x because this equation is nonlinear. Okay. Now, what we want to now do is to compare this with a simplified solution. So let's integrate this equation. Let's first linearize this equation. Now, how do we do this? There are a couple of things to understand. So if you look at the equation, the boundary condition at x equal to 0 is, it says that the slope h of x is minus cot theta e, right? So let's write down this equation again. We have h of hxx divided by 1 plus hx square whole power 3 by 2 is h by lc square. This is what we have, right? Now with the condition hx is minus cot theta e at x equal to 0 and h goes to 0 as x goes to infinity. This is the condition that we have. Now notice that if the angle, if theta e is pi by 2 or very close to pi by 2, then automatically hx is equal to 0 at x equal to 0, which means that the interface is flat. So my plate is this way, vertical, and the interface just remains flat. The angle in this case is, there is no curvature anywhere, and the meniscus height is identically 0. Okay, can we confirm this from the equation 2 that we have? The result 2 that we've got says that when theta equals pi by 2, sine of pi by 2 is 1, so that's 1 minus 1, and this goes to 0. This confirms that the meniscus does not rise at all. So what we actually see is that if theta is less than pi by 2, if theta e is less than pi by 2, h naught is greater than 0, that is meniscus rises. Okay, and if theta e is greater than pi by 2, that is it's an obtuse angle, then h naught is less than 0. In this case, the meniscus dips downward. So in other words, what we have is, this is a case where theta is greater than pi by 2, meniscus dips downwards, and when theta is less than pi by 2, the meniscus rises. So we want to also get a simpler estimate of simpler formula for the shape, because the previous result, well, let's number this equation. The previous result that is shown in equation number 3 is too complex to get any simple insight, physical insight. Now, if theta e is close to pi by 2, then dh by dx magnitude will be small, because the case where theta e is equal to pi by 2 is where the slope is identically 0. So you can expect that if you are slightly away from this angle of pi by 2, let's say you are at an angle of, let's say, 70 degrees or 80 degrees, the meniscus basically does not rise too much, and it has a gentle slope, and this gentle slope means the slope dh by dx is small. And what does it do to us? If I look at this equation, hxx by 1 plus hx square whole power 3 by 2, then I can say 1 plus hx square whole power 3 by 2 is approximately 1, because essentially I'm ignoring the nonlinear term hx square, because if hx is small, hx square is going to be even smaller, and therefore I'm ignoring this. And if this happens, then the equation essentially becomes hxx is equal to h by LC square. This is what we have, right? Now let's examine this equation. It's still a second order equation with two boundary conditions. Okay, now to integrate this, I can say let h of x is some a power lambda x, and if I substitute it, hxx becomes a lambda square e power lambda x becomes 1 by LC square times a e power lambda x. And if I want a non-trivial solution, I want to get a should not be 0, and therefore I can cancel it. Exponential terms can also be cancelled on both sides because they can never be 0, and I simply have lambda square is equal to 1 by LC square, or lambda is equal to plus or minus 1 by LC. Therefore, the general solution is h of x is some constant c1 e power x by LC plus c2 e power minus x by LC. Now, if you use the boundary conditions, it says that as x goes to infinity, h of x goes to 0, and this essentially implies that the first constant, the growing solution, goes to 0. Therefore, if I have the growing solution cannot be allowed, therefore c1 has to be 0. And therefore I have h of x is some constant, we'll call it a c2 e power minus x by LC, right? Now, if I say that this solution is valid all the way till the wall at x equal to 0, h of x is minus cot theta e, and if we do this, we have minus cot theta e is minus c2 by LC into e power 0. E power 0 is 1, and therefore c2, the constant, becomes LC cot of theta e, and therefore I have h of x becomes LC cot theta e times exponential minus x by LC. This is an important result. We'll call this as equation number 4. Let's now compare some of the predictions that comes out of this equation. One of the predictions that comes out of this is at x equal to 0, we have h of x, h naught, as per this equation, as per this result. We get, or let's basically label this, maybe we'll call it h naught of L. That is to say that it's a linearized solution. So the solution of the linearized equation h naught of L essentially becomes LC cot of theta e. Contrast this with what we had got earlier, which says that h naught is equal to LC times square root of 2 into 1 minus sine theta. Okay. Now, what we want to now do is to compare the two solutions. I've made a simple comparison for angle of theta equals 60 degrees. I'll show that now. Here I'm showing you two graphs. The blue curve is the exact solution, and that's the solution of equation number 3, and this is done for theta is pi by 3. Theta e is pi by 3, and the dashed red curve that you see here is the linearized solution. That's equation number 4. So again, this is done at an angle of pi by 3. Pi by 3 by no means is close to pi by 2, but still you can see that the approximate solution does a fairly good job at giving me the shape of the meniscus. And more importantly, you can see that the approximate solution approaches the approximate solution, as in the dashed red curve, approaches the exact solution as x becomes large. And here all the horizontal vertical coordinates are shown in non-dimensional fashion, meaning they are basically divided by the capillary length. Now, one of the interesting things that comes out of this analysis is that the natural length scale, if you see this equation number 4, the natural length scale or the characteristic length scale that emerges from this problem, length scale is LC. LC is the natural length scale because it tells us the decay rate at which the meniscus is basically merging with the far field solution. Okay. So now we have basically got the solution of the meniscus from the full equation. That's the nonlinear equation. That's equation number 3. We've also got the height of the meniscus that meets the wall. That's the exact height. And finally, we've also got an approximate solution. And we see that the approximate solution gives us a very simple, elegant result. It gives us a decaying solution, right? Now, we want to finally understand, is there a simple explanation for why the fluid rises at all in the first place? So to do this, let's again make a simple sketch of the meniscus. So here's my plate, and this is the horizontal is my, well, may not be a very good job at horizontal. Let me do that again. This is the shape of the fluid in the far field, but then the meniscus, actual shape of the meniscus would be we'd approach this far field. Okay. Now we want to do a force balance. That's what we want to do. Now, how do we do a force balance? Let's take a control volume. That is enclosing a part of the meniscus, coming all the way from minus plus infinity to some location x. Okay. So again, it's important to note that the meniscus height at any location is given by z is equal to h of x, where my coordinate system is as follows. This is x and this is z and this is my origin, right? So now we will also remember that at any arbitrary location I can actually have a local angle, that is the angle that the interface makes with the vertical, and at the wall the angle is theta e. Now let's basically look at the force balance on this control volume. Okay, so let's start by writing down the horizontal component of force on the control volume. The horizontal component of the force would be, how do I do this? For example, at this point that I'm showing it with a green dot, I have surface tension is gamma, the local angle is theta. The horizontal component now would be, the horizontal component of the surface tension force on the meniscus would be minus gamma sine theta over here, but on the other side, other end, it is the meniscus is flat and therefore I have a gamma on the other hand. So on both sides it is minus gamma sine theta, and on the other side it's plus gamma. And then I also need to take into account that there is a constant pressure P naught on top. I want the projection of this pressure from the top in the horizontal direction. So this will just be, because it's pointing the net pressure, it's a constant pressure. This projection of this pressure in the horizontal direction would simply be going from 0 to z, P naught of dz, and then I also have a pressure at the bottom, and the pressure at the bottom is not constant everywhere because the height of the meniscus is dropping. Remember that the pressure at the bottom would be P naught minus rho naught gz. That's the pressure on the bottom surface that I'm going to integrate going from 0 to the height of the meniscus. So the height of the meniscus will be 0 to z, or 0 to z is equal to h. And this whole thing has to be 0 because we are in equilibrium. And I can straight away cancel out a few terms here. So this P naught dz and this cancels out the term there on the right hand side. So I simply have minus gamma sine theta plus gamma, and I have rho naught g. Integral of z dz is just h square by 2 is equal to 0, or I simply have gamma sine theta plus half rho naught g h square is gamma. So this is nothing but, if I physically understand, this is the horizontal component of gamma, This is like a suction force which basically pulls the fluid to the left. So this is a hydrostatic suction. And we can do the same force balance in the vertical direction as well. Vertical component of force on the control volume the vertical component of the force would be, if you see this meniscus again, that the sketch that I have made. Now we had gamma sine theta minus gamma sine theta in the horizontal. Now the same thing, now we need to have a vertical as well. This quantity will be, the vertical part will be plus gamma cos theta. So we have plus gamma cos theta, right? And as you go from x going to infinity, there is, the interface becomes flat. The surface tension force does not contribute to giving a vertical push to the control volume on the far end. And I want to integrate now the pressure, the vertical component of this pressure. So I have to do an integration from going from x to infinity, because we are at some arbitrary x from the left wall. Note that the pressure is pointing downwards, so the net pressure would be negative. So P naught dx, and we're going from x to infinity. And on the other hand, we have P naught minus rho naught gz dx. So these two are the projection of the forces from the bottom, from the top and the bottom respectively, and both these integrations are going to spanning the entire control volume. This fellow will be 0, and again the atmospheric part directly cancels out, and what we simply have is gamma cos theta is equal to integral of, if I take it to the right hand side, it will be rho naught gz dx, where x goes from 0 to infinity. Okay. Now let's understand what this integral on the right hand side means. I have a meniscus. Let's say, and if I take a small strip along this meniscus, of width dx and height z, this integration, if I take this integration going from 0 to infinity, then I have the entire weight of the fluid that has basically risen, right? So if, or rather at, we can simply write this expression as gamma cos theta e, where I just say I'm taking the integration not from x to infinity but from 0 to infinity. Then we simply have 0 to infinity rho naught gz dx. And what is this quantity on the right hand side? This is nothing but the weight of the fluid below the interface that has risen above the original horizontal level. So the weight of the fluid has basically risen. And why has it risen? Because this is the vertical component of the surface tension force. So the vertical component of the surface tension force, because the meniscus is meeting at an angle theta e, the meniscus essentially is getting pulled up by surface tension and gravity is pulling it down. So an equilibrium is established because there are two competing forces. the surface tension force pulling it up and gravity force pulling it down. And this causes the meniscus to bend all the way from the wall where the angle is theta e, and the decay rate is given by the characteristic length scale, the capillary length, LC. Now clearly you can see that if theta e becomes small, meaning if the angle becomes more and more acute, the fluid would rise further and further up along the meniscus. And if theta e, on the other hand, becomes obtuse, meaning greater than 90 degrees, then you could expect the meniscus to dip down, and the right hand side also would change sign as a result. So we have looked at the shape of the meniscus in this lecture. The shape of the meniscus, we've got the solution of the full nonlinear equation. We've also got the solution of the linearized equation. We've compared the two solutions for one particular case, and then we've looked at the force balance, a physical reason why the meniscus rises. It rises simply because the surface tension force is counteracting the weight of it's pulling against the weight of the fluid. So of course there's a limit to how much fluid can rise, and the fluid rises, a few capillary lengths of the fluid would rise. It's also important to remember one thing, that this meniscus here that we're talking about is actually very, very small. Just to appreciate the value, the characteristic length scale that we looked at, the characteristic length scale of the meniscus, so the deformation of this meniscus is only a few capillary lengths. So the characteristic length scale is LC, and for air-water interface, LC is about 2.7 millimeters. So if you next time you dip a straw into a glass of fluid, in glass of water, notice the little bend that you see around the straw, and the typical length scale of that bend would be a few millimeters. That's because the characteristic length scale is the capillary length, that is 2.7 millimeters. So what we will do in the next lecture is to revisit this problem, but instead of doing a force balance approach, there's a far more elegant and a very powerful technique where we would which would involve minimization of the energy. So there are two energies in this problem, the surface energy and the gravitational potential energy. We will write down the total energy and minimize it. But then to understand the minimization problems, we also need to understand some amount of calculus of variations. So I'll also discuss about the calculus of variations, and it will be a simple primer I will give as part of the course, and I'll introduce you to the very famous Euler-Lagrange equations as well. So I'll see you in the next class. Thank you.